So there's this guy, his name was Newton. Okay? Newton was pretty cool. All right? Came up with a lot of stuff. Like he was looking at a bunch of physics stuff, and he goes, man, my math isn't good enough. I think I'll invent calculus. Right? So then he's able to do more physics stuff because he just decides, oh, I'm going to just invent calculus. Pretty cool thing, maybe some of you don't realize, there was not a standardized notation scheme whenever Newton came up with calculus. So how do you think he described his stuff that he had whenever he came up with calculus? He wrote it out longhand. He had to describe the concepts that he was getting at with his mathematical techniques. He wasn't able to just write a big high S, for an integral. He had to actually describe what it was he meant by that, right? What it was he meant by the idea of taking a sum of infinitesimally small pieces. Kind of cool. Anyway, Newton came up with a few laws of motion, all right? And we're going to look at those real quick before we get started, all right? What's the first law Newton came up with? Okay. An object at rest tends to stay at rest unless acted on by an outside force. An object in motion tends to stay in motion unless acted upon by an outside force. So this first law, a lot of people refer to this as kind of the law of inertia. Okay. Basically says stuff's not just going to start changing how it's moving unless it's acted upon by some outside force. Okay? And a good example of this is when you're driving in your car and you have a cup of coffee in the cup holder and you have to stop quickly. All right? What does your coffee do? Your coffee wants to keep going. Right? It's acted on by this outside force of the car wanting to stop, but it wants to keep going. Right? So what does it do? It sloshes up and over and out of your cup, right? So this is a good kind of pictorial, mental picture of what's going on with the law of inertia. Okay? What's his second law? What's Newton's second law? Oh, you're jumping ahead by one, but that is one of them. Yeah, so the next one is, a lot of people state it as F equals ma. Force is equal to mass times acceleration. Or if you're going to state it in words, how much something accelerates is directly proportional to how hard you push on it. Okay? To make this even more accurate, force and acceleration are vector quantities. Okay, so we're going to look at that a little bit more here in a couple of minutes. But the idea here, or a good example you might think of is, let's say you have a basket full of groceries and you're trying to get those groceries moving. So you push real hard on the handle, and what happens to the basket? It picks up speed. Okay. Now there's a whole other aspect of the basket example here, and it is, with the basket example, there is actually kind of a frictional force acting against how you push. Okay? So when you push, ostensibly you are overcoming the friction that's happening on those wheels in order to make it pick up speed. What happens if you stop pushing? Okay. Yeah, that frictional force, which is also an outside force, is going to make it lose speed, right? And it'll come to a stop at some point. This was actually kind of confusing for early thinkers about motion, right? Because everything you do in kind of a standard world system, you generally always have friction. So you get something moving, it's going to eventually stop. And so this concept confused a lot of early thinkers about motion, and they thought in order for something to move, it has to have something that continually moves it, right? And that's one of the reasons why Newton had to state his first law first, is to dispel some incorrect thinking about how movement may work, right? He said, no, no, no. In order for something to keep moving, nothing acts on it, and it will keep moving, right? So that he kind of dispelled some incorrect thinking about movement, and said how it really works is F equals ma, and it's got to pick up speed, and if there's friction, then that might make it lose speed, but both count as externally applied forces. Okay? Now, the third one. The third law, someone said here, what is that one? For every action, there's an equal and opposite reaction. Okay? The way I like to state this one is that forces come in pairs. So a good example of this is if you have a ball resting on a surface, okay, and ostensibly this is in a gravitational field. You have a ball resting on a surface. One way of looking at the interaction between the ball and the surface is to think about it from the standpoint of the ball. Okay, if you're the ball, you say, I feel a force coming from the surface pushing on the bottom of me. Okay, what if you're the surface? If you're the surface, you say, I feel a force coming from the ball pushing on the top of me. That is the same force, right? In order for it to exist, both halves of it have to exist, right? A force doesn't just come in and exist out of nowhere. It's an interaction between at least two bodies, right? So this is a good point here, that forces always come in pairs. If you're looking at a force applied to one thing, it is coming from another thing. Let's think about the gravitational aspect of this. There's a force being applied to the ball, right, due to the gravitational field. Where's that force coming from? The Earth, right? So you might say, as the ball, you might say, I feel this force acting on me coming from this gravitational field, which is basically an attraction to the Earth. But if you're the Earth, you might just as well say, I feel this attraction moving toward that ball, right? There's always two halves of a force. Anytime there's one force that exists, there's always got to be two. All right. So what we want to do is we want to use Newton's laws and be able to handle situations where we can observe that there is no acceleration happening. Okay? We stated at the beginning of this course that we're going to study statics. Okay? Statics, means no acceleration. Okay, if there's no acceleration, what does that do to our F equals ma? Okay, what we're doing is we're saying A is 0. Okay, now what's interesting about this is that when we have A equals 0, since it is a vector quantity, that means that all components of that vector have to be 0. That means if it is in a two-dimensional system where you have x and y, it means that both the x and the y components have to both be 0. Okay? So what this tells me is that F is equal to 0. 0 vector means all components have to be 0. And this means that if we sum up all the forces all the x components of force that we have, they have to sum to 0 if we know that we have a system that has 0 acceleration, right? If we have a system that has 0 accelerations, we can also sum y, and it has to be equal to 0. This is our condition of equilibrium that we have. So and this is for 2D. This is 2D equilibrium. All right, what if you have 3D equilibrium? Okay, you do the same thing, but you also have to have 0 force. The sum of all the forces in the Z have to also sum to 0. All right, And this is, by the way, for the case where we have a concurrent force system. That won't mean a whole lot to you until we start talking about non-concurrent force systems, but I'll just go ahead and put that in there now and say this is for a concurrent force system. And a concurrent force system is one where the lines of action of all the forces applied to the system all intersect at a common point. Okay? They don't all have to work that way. Not all force systems are like that, but you know, this works for those types of force systems. All right, so what we need to do is come up with a technique to use this expression, right, or these two expressions, sum of forces in the x and sum of forces in the y, both equal to 0. Here is our best tool we have for doing that. It is called free body diagrams. Okay? The concept behind free body diagrams, it basically follows through Newton's laws. All right? What we do is we understand that Newton said that if no forces are acting on a body, then it is not accelerating. Okay? So our first step always with our free body diagrams is we first need to think about what body is it we're trying to analyze, and then mentally we have to take that body and make it free. When we say free, we say, you know, not under the influence of anything. It's like it's floating out in the middle of space somewhere. Okay? So I'm going to do this for a particular kind of example. Let's say that we have a weight that is hanging from a couple of ropes. Say that there's a rope that goes up to a connection point up here, and there's another rope that goes to a connection point right here. So right now, that body is not free the way I have it drawn, correct? Why is it not free? Because it's connected, right? It's connected to the anchor points. By the way, anytime you see me draw something like this where there's a hatching, you know, this basically means like anchored or fixed. That's what that, you know, if I draw something that looks like that, that's what that means. Okay, so this body is not free because it is hanging from ropes. Okay, so our first step for our free body diagramming is actually this. Identify the body or bodies that you will be analyzing. Okay? Here's how you do that. You kind of have to look at it and say, what is it that I want to know? And usually what you have to do is you have to free the body from the constraints where you want to know what the values are, what the values of forces that are being applied by those constraints. So in our case, what would we do? We would say, what's the body that we need to free? Yeah, the little weight that's hanging from the two ropes. You need to free that body. To free the body, what do? You disconnect it from the ropes, right? So that's kind of the first step is thinking about what we want to do and how we want to end up analyzing this. When you free it, you basically draw that body free from all interacting bodies. So that's step 2. So draw a sketch. Of the body free from all other interacting bodies. So that's what I did for step 2 right there. Step 3 is where most of the thinking has to go in. Okay? What we're going to do now is replace the influence or influences we removed in step 2. We replace them with force vectors. Okay? So not only did we free it from the ropes, we also kind of freed it from the effect of gravity. Right? This picture that we've drawn right here, mentally we have that floating in space now. Okay? What are we going to do now for step 3? Okay? We'll show force vectors. Okay? And those force vectors are going to act in the direction of the forces that were originally applied. Okay? Now usually what you do is you try to name those force vectors in such a way as they are descriptive. So let's say that, you know, over here this was rope A and this was rope B. Okay? If that's what we had called those things in the original, then I might say that this is FA and this might be FB. Okay? And this is starting to get into the last step. Actually, there's one other force that I need to put on here. What would that be? Yeah, the force that acts on this thing due to gravity. And so I might call that something like weight. Okay. But I don't have enough information yet to figure out what FA and FB are going to be, even if I knew the magnitude of the weight of the thing that's hanging from the ropes. What else do I need to know? Yeah, you need to know something at least about the geometry of how it was hanging. Now, is that something that if this was a real weight that was actually hanging from the ceiling up here? All right. Would there be any kind of a way that you could come up with the directionality of those two forces? Yeah, you could measure it, right? You could maybe use a protractor. A lot of tools out there are available to measure slope. A lot of you may even have that in your phone. All right. I have an app in my phone that I can take the edge of my phone and stick it against someone and it'll tell me what the slope is of the edge of my phone. All right. Or a degree measurement relative to vertical. All right. So that kind of stuff is available and you could measure that. And so usually to do that, you would need to have a coordinate system established, and maybe you would know something like, what are these directions of these two ropes? Okay, so I might call this like theta B and theta A. Those are things that you could possibly measure based on the actual situation that you are working with. Okay, so whatever of that kind of information you need to apply, make sure you copy that stuff over onto your free body diagram. Okay, and I know that these two diagrams look very similar, but I'm trying to draw as many distinctions as I can between them, because when we're working in school, we basically express to you all the problems we want you to solve. We express them to you on paper, which means we got to give you all this information on the piece of paper, and that ends up making the free body diagram look similar to the given information, right? But real life is different, right? In real life, you might have to go out and there is no piece of paper yet, and you have to draw the piece of paper about what the original situation is, and from that, come up with what the free body diagram would look like. Okay, so I just want to try to orient you to why these two are different. What I call this right here, this is a physical scenario. Right, down here, this is a free body diagram, or FBD as we often call it. And so what I did in that last step, I didn't really label this yet. We basically include all lengths, angles, slopes, and any other, if there's anything else that's pertinent as far as the geometric information that's given to you, you need to make sure those are copied onto the free body diagram. Okay? So that's how you draw the free body diagram. What do you do with the free body diagram once you've got it? Okay, so once you have your free body diagram and you've included all the things that you know on it, you should have all the information right there on the free body diagram in order to go on and write equilibrium equations, which is what I mentioned up here at the top. Okay? But don't start writing the equations until you've done the free body diagram. That's a recipe for disaster. Okay? Why is it a recipe for disaster? Here's why. Free body diagrams are those kinds of things. It's a little bit like a frog boiling in a pot. All right? Many of you, in fact, I would even guess most of you, for a problem like this, would get the right answer just by immediately starting to draw or write the equilibrium equations. All right? Most of you could go straight from the physical scenario, write equilibrium equations, and get the right answer. Would you say that you feel like you could do that? Okay, I think that you can too, all right, for this problem. What happens though? The problems get different. Okay, so when the problems get different, at some point you won't be able to, and you haven't practiced the steps of how to draw the free body diagram. The free body diagram will allow you to solve problems that you are unable to handle just by mentally trying to deal with them. This is why preaching the necessity, the importance of free body diagrams is something that I am not the only engineering instructor in the world that does this. As a matter of fact, I think all of them do this. The free body diagram is incredibly important, and it's because you won't know that you need it until you need it, and if you haven't been practicing it before you need it, you won't know how to use them, and it's going to be a problem. Okay? So, practice using them. Now, shall we do a quick example problem? All right. It has to be really quick because we don't have much time left. So, why don't I just do the problem that is shown here? But I'll do it with real numbers. Okay, let's say that we have a weight. I'm going to do it this way just to really emphasize this point. Okay, let's say that this weight is 10 pounds. And let's say that this angle over here is, I don't know, let's say 25 degrees. Let's say that this angle over here is 30 degrees. Okay, and what we need to do is find, let's say that this is rope A and rope B. We need to find the tensions in ropes A and B. All right. We have 5 minutes. What should we do first? Draw a free body diagram. Okay. We've already talked about this one. We isolate the body. Okay. We're thinking of it being removed from all interacting forces. What's next? We put back the forces, right? But we do them as force vectors. Then what? We label them. We say this one's 10 pounds. This one up here we'll call FB because we don't know what it is yet. Over here we'll call this FA because we don't know what it is yet. And we copy all of our geometric information that we need over to here. This is 25 degrees. Okay, over here, this is 30 degrees. That's my X and Y coordinate system. Okay, so what I did is I went from my physical scenario to my free body diagram. Now what? Okay, we can go to our equilibrium equations. Okay, our equilibrium equations, we first sum forces in the x direction. Okay, what do I have there? Okay, so what I'll have is, I'll say minus, FA is the total magnitude of the force in rope A, right? But I don't want the total magnitude, I want just the x component. So I do what? Multiply by the cosine of 30 degrees to get just the x component. Then I have FB that points to the right, so I say plus FB times cosine of 25 degrees. Why am I using cosine for both of those? Yeah, I'm trying to get the adjacent component, right? Cosine always goes with adjacent, so I'm trying to get the adjacent component in both of those cases. Do I have any other forces that act in the x direction? I do not. Okay, the next expression that I want to write is a sum of forces in the y direction. Okay, so for that, what do I have? Okay, positive FA sine of 30 degrees plus FB okay, minus 10 pounds. Why minus? It goes downward, right, which is opposite the direction I'm assuming is positive. And that was actually something I did right at the beginning. Some of you may have noticed, but I made it extremely explicit over here what direction I was taking to be positive. All right? I encourage you to do that because it just basically makes it unmistakable, undeniable, right? This is the direction you're taking as positive. All right, so these are our two expressions. They basically form a system of equations. And at this point, you should thank everything that you hold dear that you don't have to actually do those systems of equations. You can just use your calculator. So here's what you do. Mode 5 in the Casio calculator. If you look at that, the first entry implies that you have a 2 by 2. X and Y are the two unknowns that you're dealing with there. And you need to put in, for each expression, you need to put in the coefficients of X and Y as well as the constant term. And you need to put them in this order, right? If you're using the Casio calculator, you need to put them in so that you put your coefficient of X, coefficient of Y, and then the constant you need to have as if it was on the other side of the equation. Okay? So we'll keep that in mind as we put in our numbers here. So here I'll put in negative cosine 30. That's the coefficient of my first variable. What's the coefficient of my second variable in my first equation? Cosine 25. Okay, what's my constant term? 0. What is the coefficient of my first variable in my second equation? Sine of 30 degrees. And I have my calculator on and of course my stylus goes nuts. Okay. Then I have positive sine of 25. Now, do I put in a negative 10 or positive 10? Positive 10, because I need to make it match the form that it's looking for that it mentioned in that menu. right? So I put in a positive 10 instead of this negative 10. When I hit equals, x, which is the first variable I was looking for, that's actually FA, is 11.06. Oops. 11.06 what? Pounds. And FB, you hit equals again, FB is 10.57. And you have figured out what the two forces are in your ropes. You should keep that one maybe in your shop or someplace where you're not doing real math, and get yourself either a TI 36X Pro or a Casio FX 115 ES Plus. One of those two calculators are going to do the best for you in terms of being able to solve more interesting things. FX 115 ES Plus. You can only go up to a 3x3 in these calculators. I will say that when I design tests, I know that, and I'll leave it there.